Hello, my name is Hannah Kajowski, and I'm the team lead for the Galileo Rover team at the University of Colorado, Denver. Our team consists of 5 mechanical engineering seniors and are pictured here. From left to right is myself, Brooke Grossman, Killian Moran, Evan Rubio, Jaime Rodriguez, and lastly not pictured, Aaron Lee. The NASA Human Rover Challenge is an international competition that simulates extraterrestrial terrain through a series of challenges within an obstacle course. These challenges consist of various tasks that relate to those similar of astronauts and unmanned rovers. The objectives of the competition and the Galileo Rover project is to bring a first place win to CU Denver. In order to meet the objective of being the overall winner, the rover, in collapsed form, must fit within a 5x5x5 volume box constraint. We must optimize the linear steering system and complete the assembly of the wheels. The primary objective for the Galileo Rover steering design team was to ensure that the linear steering design adhered to Ackermann geometry, in which during a turn, the inner wheel is sent a smaller radii than the outer wheel, as to avoid wheel slippage or skidding. There was also a priority to eliminate any single shear connections to improve stability, and a goal to redesign the handles to improve a more comfortable steering experience for the driver. The steering design was formed on the basis of 2 parallelograms, offset linearly with the base of the handles connecting them on each side. 2 tie rods were chosen to connect to the middle of the base of the top steering arm and extend diagonally to the wheel knuckles. These were designed so when the driver pushed the left handle forward, the right would go back and angular directions would be sent through the tie rods to the wheels, with a smaller radius being sent to the right wheel. The attachments connecting the steering and suspension arms to the wheel knuckles were redesigned for double shear connections. By looking to improve the handle design, a 3-tier design was chosen. The design was made to connect the 2 steering arms linearly and then extrude up and in towards the driver. The handles underwent a few design alterations before the one in the picture was finalized. And finite element analysis was used to confirm that this on the right would support the maximum force needed to drive the vehicle before any manufacturing and welding was completed. The rules for the competition required the rover to climb 30-degree inclines through various obstacles. Using the recorded power output between the 2 riders and the weight of the loaded rover, we calculated how fast the rover could travel on a 30-degree surface based on power to weight ratio and vertical velocity. We assumed that the riders could maximize power efficiency if they pedaled at an angular velocity of 72 RPM. The final drive should have allowed the riders to pedal at this speed in 1 gear, while the rover traveled at the calculated velocity. Based on these calculations, we decided that the final drive should be 2. Point 2. One of the gearboxes had a 32-teeth sprocket attached, which would require a 70-teeth sprocket on the drive shaft to get the correct final drive. Previous teams used sprockets that required a 9-spline and a 6-bolt fitment. The issue with this was that only 22 teeth sprockets were available for this fitment style. Second gearbox required a 4-bolt fitment, and the smallest available sprockets had 39 teeth. There was a sprocket in the shop with these specifications, so it was installed on the gearbox. This set of sprockets limited the acceptable surface angle to about 7 to 9 degrees. To reduce the weight of the rover, hollow aluminum pedal posts and hollow carbon fiber stringers were designed. Through software for simulations such as Fusion 360 and SolidWorks, it was determined that the carbon fiber and aluminum 6061T6 materials would yield lightweight parts with a safety factor of 3 while reducing the overall weight of the rover's frame. Other components such as aluminum 6061T6 bulkheads and carbon fiber torsion plates were designed with the same goal in mind in order to provide structural support for the steering and suspension assemblies. The combination of these components created a frame strong enough to sustain 2 riders while reducing the weight of the rover. A hinge folding mechanism on the pedal post was designed to allow the pedals and gearbox to be folded and locked on itself to reduce the size of the rover frame from 10 feet to 7.5 feet. The rear suspension can also be folded into the frame of the rover or locked for the rover to be operational by using a spring-loaded latch pin. The wheel sub-team designed and manufactured wheel spokes to adhere to the outer portion of the carbon fiber on both sides of the wheel. This was made of aluminum and secured with bolts. The decision to add these strengthens the overall integrity of the wheel at the hub shaft and prevents possible oil canning and potential failure. The final wheel assembly can be seen on the right-hand side with the aluminum spokes added to the wheel along with the foam and outer rubber tread. During the competition, certain obstacles contained optional tasks for additional points. These task tools consisted below were designed and manufactured, but unfortunately could not be implemented due to a virtual competition. Unfortunately, after final decision by the NASA staff, the competition was held virtually this year, with the option of video submission, in which Galileo did not meet this deadline. Although that objective was not met, the team successfully welded the hinge mechanism, meeting the requirement of the rover fitting within the 5x5x5 box. Once the steering system was assembled with the knuckles and axle, the tie rods were able to successfully translate the linear motions directed from the handles into angular directions for the wheels. Due to time constraints, further testing was not completed to ensure that the steering design prevents skidding while turning the vehicle. As for the handles, after welding and assembly, it was realized that they sat much lower than anticipated. As such, they encroached on the driver's seat and hampered the ability to drive. Although various pieces of the Rover needed final touches, the vehicle is completely assembled and therefore completing our team's internal objective. For the parts that are left to be completed, we believe that the analysis we did shows the final product would allow the rover to be fully functional. On behalf of myself and the rest of the Galileo rover team, thank you for watching.